Hello, Honors Chemistry, and welcome to your Chapter 12 review. So obviously, Chapter 12, huge amount of qualitative material. Please go review that and make sure you know that, right? And if there are things from your outline that are fuzzy that maybe you should have come to ask about but you didn't, right, as you're reviewing, right, that's a great time to go ask those questions so you can make sure that before the test gets here, you are good to go. All right, so we're going to start our Chapter 12 review by talking about IMFs because really everything else in the chapter is based on the concept of IMFs. So let's start here, where IMF stands for, right, intermolecular forces. Yes, where inter means what? Between, right? So these are the forces in between molecules, intermolecular forces, right? And this is what holds any one molecule to its neighboring molecule, right? And your book goes over 4 types of IMFs, right? Where we have our London dispersion forces, we have our dipole-dipole forces, we have our hydrogen bonding, and we have our ion dipole forces, right? Where in general, this is the ordering in terms of strength, okay? Now, what this really is it's a measure of polarity, right? Where these are the most polar, or these are the most polar interactions, right? And these are the least polar interactions. And that's basically what this is a scale of, right? Where if we think about what a London dispersion force is, what is it? Right, it's a temporary, transient, fleeting polarity, right? It's an instantaneous dipole, okay? So we have an instantaneous dipole. I don't feel like spelling the whole word out. Instantaneous dipole, right? And it applies to anything with electrons. So if it has electrons, it has a London dispersion force, which means that, right, everything has London dispersion forces, okay? Because, like your book talks about, right, at any given point in time, the electrons, so we're talking about total electrons, within a molecule might be unequally distributed. And if they are unevenly distributed, right, if more of them are on one side than another at an instant, then for that moment, that molecule has a dipole, right, an instantaneous dipole. And then it will induce that in its neighbor, which then induces it in its neighbor, right? And so we get a moving instantaneous dipole throughout my substance, right? So instantaneous dipoles happens to anything with electrons, and its strength is based on the total number of electrons, right? So something with more total electrons has a stronger LDF, okay? So then we might think about dipole-dipole forces, right? Where dipole-dipole forces apply to, right, polar molecules, which means what? Right, which means we can't evaluate if something has a dipole-dipole attraction unless, right, unless we draw a Lewis structure and assign it a 3-dimensional shape based on our Vesper table, which means, yes, you need to review that and make sure you know how to do that, right? So polar molecules have dipole-dipole forces, right? The more polar a molecule, the stronger the dipole-dipole, right? Which we didn't really get much into when we did our Vesper tables, so that's fine, right? So polar means it has a dipole-dipole force. Hydrogen bonding is like a very polar molecule, right? Where the definition was we have to have a hydrogen bonded to an F, O, or N, right? Hydrogen must be bonded to an F, O, or N, and then that hydrogen is attracted to lone pairs on neighboring F, O, or N's, okay? So if we think about what that means, if we think about water, for example, right? This hydrogen is bonded to an O, part 1, and it's going to be attracted to the lone pairs on a neighboring oxygen, yes? Hydrogen bonding, right? Must meet that whole long definition. Okay. Right, hydrogen bonding. And then we have our ion-dipole interaction, which we're only ever going to talk about when we have an ion and a dipole, which for our purposes is going to mean ionic compound in water. And this explains why ionic compounds dissolve readily in water, because this is a very strong interaction, right? And it's a direction-specific attraction, right? So for example, if I dissolve sodium chloride in water, I'm going to have sodium ions and chloride ions, right? And what it means to dissolve, right, means that substance A has a way to interact with substance B via a shared IMF, right? And that's what this is, right? When we have our sodium and our chloride, what that means is that this is positive, so the negative end of water is going to surround it like so, right? Here, this is the negative end, right? So that means the positive end of water will surround that, right? And then we'd have more and more. And so what happens is we get a shell, a hydration shell, right? A shell of water molecules directionally specific, right, around each ion. Yes, and that's what dissolving means, right, for an ionic compound. If it's a non-ionic compound, right, we still have to have the same idea, right, where there has to be some way to interact. So if we were to think about water, for example, and ethanol, right? Well, let's do methanol. It's a smaller molecule. All right, so if we look here, what are my options? Right, if I want to decide if these are going to dissolve, I have to make sure that they have some kind of shared IMF, right? So this is polar, this is what? Right, this is tetrahedral around here, but they're not all the same, polar, right? So they're both polar, so they have dipole-dipole forces. What else if we evaluate carefully? Right, they are both capable of hydrogen bonding. So if I ask you, are these going to dissolve? Probably, because they're both polar, they both have hydrogen bonding. Yes? All right. Whereas if we were to take something that was just water, for example, and some butane, if we had this, right, nonpolar, polar, are they likely to dissolve? No, the answer is no. Okay. So anyway, this is a summary of types of IMFs, right? The strengths of my IMFs, and how we can use that to decide if one thing is likely to be soluble in or miscible with some other substance, right? They have to have a shared IMF, a way to interact with one another, right? The last thing to remember, right, is that these are, there are a lot of other things to think about. For example, right, when we talk about this is my relative strengths of IMFs, right, that also dictates other properties like what? Right, things that have stronger IMFs will have higher boiling points, higher melting points. They are more likely to be solids at room temperature, right? But we have to remember, right, that these are one, summative, right, which is part of why water is so special, right, because water has LDFs and dipole-dipole and hydrogen bonding, right, which means its strength of attraction is stronger than, right, a lot of other things because it has all three of these. Okay, but there are certain nonpolar molecules that have so many total electrons, like C60, for example, right, with its accompanying hydrogens, is a solid at room temperature and has a really, really high melting point and boiling point because there are so many total electrons that at that point that London dispersion force is quite significant. Yes, does that make sense, right? So we do have to stop and think about big picture things, right? So if you were asked to compare, right, so for example, if we were talking about the melting point of xenon versus the melting point of, let's say, something CO, for example, right? Xenon versus CO. We might say, oh, well, this is what draws Lewis structure, right? This is polar, right? This is, well, it's not a molecule, right? But London dispersion forces apply to these, right? Because something has to hold them together, right? So this only has LDF. So if we're thinking about it, right, this we would think would have a higher melting point. But if I tell you this one has a higher melting point, you should be able to justify why it would have a higher melting point, right? So you could go look at a periodic table, figure out how many total electrons xenon has, which is a boatload, right? And then say that in this case the LDF is stronger than this dipole-dipole because of the total number of electrons. Yes? Okay. All right. I think we're going to pause here and we'll pick up with the rest of our Chapter 12 topics, which are all based on IMFs, in the next video. All right, thanks for listening. Be good, and I'll see you soon. Bye.